So anyway, it's not a waffling. I'll put it on a longevity test now, and I'll put the back on, heat it up. I might put a temperature probe. The bottom of the heatsink's about there, and the main part of the component is about there. So if you remember the two memory chips, the center of the chip was just slightly above that second chip. So that puts it around about there. Okay, so that's going to be my testing setup. Assume you can read the screens. Got some reflections of the lights, but yeah, basically both probes were started off about a degree with each other. The other one went up, the red one, the one that's on the heatsink, went up by about a degree when I pushed it into the case. Hasn't been on, so obviously the heatsink is just picking up more room temperature than what the internal sensor is on the 10 mark, the one on the left, or the orange one. And I'll switch it on and watch it for a little bit, and then just do a montage of photographs of before and after. Okay, so what I'm going to do is I'm going to do a stress test. This is about the second time I've done a stress test, but I will do that on camera now. Let's see whether the thermal stress on the chip, on the BGA chip, is going to crack a connection. Now, when I did the reheat, I did not heat the BGA chip so that it would move. So there's a possibility that I've only partially fixed the problem, and by thermally stressing it, well, let's face the fact that it became faulty due to faulty the thermal stress to begin with. It just took 3 or 4 years for it. With my fix, because I'm a little bit skeptical about the effectiveness of the work that I did. This thermally stressing it could get it to fail early, and it could actually reduce its reliability, so that whilst it leaves here, I've actually reduced its field service life. But anyway, all right. So here we've got the chip. Just to orientate ourselves, there's the device is about there on the thing. This is my LGE35230 freeze spray. Ambient temperatures come down a few degrees to 25 degrees C, and we're still 60 degrees on the chip. So what I'm going to do is in the void of that heatsink. If you remember, the heatsink had fins here, and then a void, and then fins again. What in the void, in other words, not directly above the heatsink, I'm just going to provide some half-second bursts for about every second or so, and we should be able to see. I hope you can read the meter. It's a bit shiny on the screen, so I'm not sure whether the glare is going to affect it or not. But let's start doing it. We should start to see the chip temperature dropping. Actually, I'll turn the volume up just in case I can hear anything funny going on. I'll go down to about ambient. We'll see how long it takes to recover. Now, remember, I'm not actually cooling the chip. I've gone a little bit below ambient. How far down do I want to go? Stop at 18. There we go. 17. Still going down. 16.5 degrees Celsius. Starting to come back up again. So that's I'm cooling the heatsink down. The heatsink is attached through a thermal pad, or actually some heatsink compound and a silicon pad, to the top of the device. The device is internally the casing of the device is attached to the chip, and there's thermal resistance between each of those interfaces. So I've at least taken the chip down to about 30 degrees now. It's arguable whether I've affected any temperature or any significant temperature change down at the BGA interface, because I'm measuring the heatsink. I suppose if I wanted to go further lower, I could continue to do it. I don't want to use up all my free spray. So I've taken it down to about 12.5 degrees. And it's still operational. So I was interested to see whether and how much a difference adding a fan might do. So this has been running for over an hour or so, whereas the original setup without this poxy little fan that I had, it was at 60 odd degrees with an ambient a couple of degrees warmer than that, or a degree warmer than where it is currently. And with that's a little 40mm fan that I've dug up. It's really old. It runs off 5 volts. Originally it was designed as a 486. I don't know whether any of you Intel people might remember the 486 processor, but it was a fan that used to sit on the top of designed to sit on the top of a 486 processor. So it just runs off 5 volts. It's spinning really slow. I'm not sure how fast it's actually spinning. I suppose I could do some tacho measurements on it and find out how fast it's actually spinning. But that aside, I was interested to see how much any additional airflow might do. I suppose if you really wanted to, you could leave a epoxy fan like that on the outside. Put in screws. I mean, the screws almost line up with the holes for the 40mm fan, so you could jury rig it. I don't particularly want to do that because I'm pretty much going to guarantee that's going to get ripped off as I'm trying to transport it. But yeah, so that's interesting. It's a good 10 degrees cooler.
Okay, so I think I'm pretty much done with the temperature testing, so I'll go back to using the serial interface, but this time I'll record it. So with my experimenting with the serial interface, I ended up finding a website. Yeah, that should be it. LGE35230 BGA. This has all kinds of weird and wonderful. Well, it has useful information. Being a Russian site, I'm running it in a restricted browser. Doesn't hurt to be at least a little bit cautious. And it goes into this RS-232 connection. So I've got an just a USB serial here, and I've got my agenda changer to go, because that cable's not long enough, so I ended up using a 1-to-1 cable, and then I needed a agenda changer, and so I made just a 3-wire agenda changer there, as per this configuration here. And well, I didn't need that, but I mean, that's completely familiar. But anyway, in the process of mucking around with these debug modes, I came across a section, bootloader connections. So it says start the term emulation and set it to 115 well, it's not baud rate, it should be bits per second. Baud's a different thing altogether. Anyway, but you get the idea. This being a Broadcom one, they have this thing called a CFE bootloader, and I did download some documentation for that, and I haven't really sort of spent a hell of a lot of amount of time about this common firmware environment, originally designed by Broadcom, yada yada yada. Having said all of that, this model, or this revision of the firmware that's in this TV has got most of this stuff disabled. So they get you to connect like this, and then hold down and press this key, the back tick. On most keyboards, that's the key below the escape key in the top left. So on my keyboard here, I've got the tilde as a shift function of that back tick. Interestingly enough, it being so close to the escape key, it's the conspiracy theories start, because I think in earlier models they did tell you to hit the escape key, and on this one they've chosen to use the back tick. So anyway, the side of one of the things that I found is, in trying to get to that, I can actually sort of simulate at least the startup conditions that I had in the original fault on this TV. As a rough guess of what's actually happening is this, because this serial connection goes through that MICOM chip, and that MICOM chip has all kinds of weird and wonderful functions, which I will show later, but you can do things like turning the inverter off just using the MICOM chip. Well, yes, I suppose it does, because I couldn't get into anything else, but I suppose that the MICOM chip is actually talking to the main program on the system on the chip, the Broadcom chip, to do that. But it is under a menu specifically for the MICOM. Anyway, the MICOM obviously has firmware on it, and when you hit that backtick on here, it must be waiting or scheduling or something to that effect for the Broadcom to wake up and get into this, because during bootstrap, you need some way of being able to halt the boot process, because that's what this is all about. And so clearly the MICOM will sit there for, I didn't time how long it was, but it was a good number of seconds. So rather than yapping, let's show. Here I've got a little mirror reflecting the power on light. In the background I've got a little mirror, so you can at least a part of the screen. I might change that aerial, doesn't matter, I'll leave it for the moment, I'll change it later. And basically go into my terminal emulation. So I've got Tera Term. I'm using Tera Term because it's got this replay log. I have been using PuTTY, but the advantage of this replay log is that I can actually see the ASCII color coding when I use that replay, which reminds me, two things I need to do. One is I need to check the serial port and change it to 115.200, 8 bits, yada yada. And let's go to the logging, get rid of plain text. I don't have anything in the screen buffer at the moment, so Tera Term log, that'll do. Let's go with that. And the instructions were to hold down the key, presumably enabling or engaging the key repeat, but I'm not going to do that. I'm just going to, actually what I'm going to do is rattle away at two keys. What I found is that enter key seems to be a special key, and often, well, I found that when you're trying to, like pressing F9 and all, which I'll show you later, you will have to proceed at least once with a carriage return, and so what I'll do is I'll just alternate between this backtick and carriage return as I'm powering it up. So let's do that. And it's made a liar out of me. Alright, let's try it again. I'll just hit the backtick. Rattling away on the backtick. Ah, there we go. You can see that red LED slow blink. That's the symptom that I had, and if I leave that, it will eventually time out, and the main part of the Broadcom program will continue to boot, I would suspect. And there we go. So there was the timeout. So yeah, interesting.
Okay, so after about a week, she crapped out. Became extremely intermittent, and the screen basically went yellow. So I've pulled the board out, the main board out, pulled the heatsink off, using the 3mm hex as usual, and I've got my convection oven on in the kitchen at the moment, and I've already done a series of tests on the temperature, so I'm going to set it. It's really old oven. Anyway, it's marked in Fahrenheit, so I've set it to basically 200. It's got an old mechanical thermostat. It's set it for 200 Fahrenheit, and I've run some tests with my multimeter with my temperature set to min-max, and it's got about a 30 degrees C regulation on it, so I'll show some pictures of that later. So what I'm doing is I'm going to put this whole board in the oven for a few minutes, and let's get this app going. Come on, turn on. Stupid thing. So what the plan here is I'm not going to take this board up. There's two reasons why I've set it to 200 Fahrenheit, and in this case, because it's a 30 degree C regulation, it's going between about 97 degrees C to about 127 degrees C. I don't want to go much hotter than that for a number of reasons. First is this plastics. These sorts of plastics, I'm not completely certain how long those plastics, what temperature those plastics will start to deform at. I'd suspect anything above 150 degrees C is going to be a problem. So I'm not going to go anything higher than that, because the regulation on the stove or the oven is not very good. I'm going to keep it down quite low. The second reason is some of these components are usually rated like 105 degrees C max, continuous, and then there's thermal envelopes and profiles and all that kind of stuff. Now I'm going to use this again, but I'm going to run it at a much higher rating, and the aim in this case is to get the BGA package to move around. And I'm going to cut a bit of solder off as well, I think, and I'll drop it on the top of the chip. Well, we'll see when I come to it, because if it doesn't start to move around quickly, I will. Alright, what I'm going to do is use my El Cheapo head thing. I shot some skiing videos with El Cheapo, not like a hero because I didn't think the thing was going to last very long, so I only spent like $80 on it. Okay, so I'm just going to get it out of the oven now. It will be a little bit delicate, but it's not really hot enough for it to be overly concerned about mechanical. Hopefully that stupid thing's recorded. Stop. Reset. Start. Should have prepared a little bit better than what I have, but anyway. Zoom in. Yep, should have prepared better. Where's my cutter's gone? Damn it. That solder melted straight away. Okay, even though I haven't seen the chip physically move, doesn't mean it hasn't moved. I'm getting old and I haven't got the right equipment. So I've had enough. So it was about 7 minutes in the oven at peaking at about 120 something degrees, and another 4 minutes there. So I'll let that cool down, and the ambient temperature's gone up to 28. Okay, I think that's cooled down enough. Yeah, there's the solder ball. So I'll just put the heatsink back on, clean this up, put the heatsink back on, and give it a test. So the board has a slight bow in it, so if I were to do it again, I'd probably put some support under here. What I'm going to do is with those clips are pretty ordinary, so I'm just going to get in there on either side and push out the little wing tips out. Just so that they actually do their job. Yeah, not very good. Right. Squeeze out the heat sink. Compound, because the idea of the hot heatsink compound is you want it to transfer heat, and the easiest way for that to happen is for it to be as thin as possible. The bow's not too bad. Okay, so switch it on. The red light. And yay, success. The aerial's not so good.
It was then a bank.
I'm on low power, it's like we're about 40 watts at the moment. If I hit this energy button, we're up to 60, 70, 80 watts. Where are we? Off. So that's 120 odd watts. 120, yeah. And where are we? Minimum, medium, maximum. And we're back down to 40 watts. Cool.